By noon, the road is too hot to touch. Black asphalt has been absorbing sunlight for hours. The roof above it is storing more heat. Glass towers are reflecting radiation toward the pavement, and every air conditioner is pushing additional warmth back outside. But beneath the same district, thousands of tons of cold water are moving silently through insulated pipes. On the roof, a bright coating is reflecting sunlight before it becomes heat. Across the street, shade, mist, and carefully directed airflow are lowering the strain on pedestrians. China has not discovered one secret machine that makes summer disappear. It is experimenting with something much bigger, a city designed to intercept heat at every stage. Before it enters a building, before it becomes trapped in a road, before it overwhelms the electricity grid, and before it reaches the human body. Today, we are going inside China's layered urban cooling strategy. What genuinely works, what has been exaggerated, and why cooling the cities of the future will require far more than installing additional air conditioners. Subscribe for more premium documentaries about China's infrastructure, engineering, and future technology. The story begins early in the morning. At sunrise, the city may still feel comfortable, but millions of square meters of roofs, roads, walls, and windows are already interacting with solar radiation. A light natural surface reflects part of that energy. A dark road absorbs much more. The energy enters the pavement and raises its temperature. The road does not release all that heat immediately. It stores part of it. By afternoon, the surface can become far hotter than the surrounding air. Then the sun sets, but the road remains warm. Heat flows back into the streets throughout the evening. Buildings do the same thing. This is one reason dense cities can remain dangerously hot at night, even when nearby rural areas cool more quickly. The city has become a thermal battery. Air conditioning protects the people inside selected rooms, but it cannot erase the heat stored across the entire urban landscape. In fact, conventional cooling moves indoor heat outdoors. Thousands of compressors operate during the hottest hours, increasing electricity demand precisely when the grid is already under pressure. In heavily air-conditioned regions, cooling can represent the majority of peak electricity demand during severe heat waves. China's emerging response begins with a basic principle. The cheapest heat to remove is heat that never enters. That leads us to the roof. Ordinary dark roofing absorbs a large share of incoming sunlight. The hotter the roof becomes, the more heat moves toward the rooms below. Insulation can slow that transfer. A reflective surface attacks the problem earlier. It sends more solar energy away before the roof has a chance to store it. But researchers are developing coatings that do more than simply appear white. Passive daytime radiative cooling materials are designed to perform two tasks. First, they reflect a very high percentage of incoming solar radiation. Second, they emit thermal energy strongly within specific infrared wavelengths that can pass through the atmosphere. In simplified terms, the surface rejects sunlight while releasing part of its own heat toward the cold sky. Under suitable conditions, a surface can remain below the temperature of the surrounding air even while exposed to daylight. That sounds almost impossible, but the underlying physics is well established. The challenge is turning laboratory performance into a coating that survives years of dirt, rain, ultraviolet exposure, and changing weather. Recent Chinese and international research has focused on making radiative cooling materials more resistant to humidity, environmental aging, and real-world contamination. Because a brilliant white sample on a clean laboratory roof is one thing, a coating on a polluted building after 5 summers is another. Dust lowers reflectivity. Moist air reduces radiative performance. Clouds restrict the path through which heat escapes. And a roof coating cannot automatically lower every room by the same dramatic number shown in a promotional video. Its impact depends on insulation, ventilation, roof area, and how the building is used. Still, at enormous urban scale, small improvements matter. If thousands of roofs absorb less solar energy, thousands of cooling systems face a lower load. The city stores less heat. The evening becomes slightly more survivable. But roofs are only one surface. The road below may absorb even more energy. Traditional black asphalt is durable and familiar, but its dark color makes it an efficient solar absorber. During severe sunshine, the surface may reach temperatures capable of damaging skin and increasing heat exposure for pedestrians. Cool pavements attempt to change that equation. Some use lighter or reflective coatings. Others use aggregates selected to absorb less radiation. Porous pavements can temporarily hold moisture, allowing evaporation to remove heat. Tests often show substantial reductions in surface temperature compared with dark, untreated asphalt. But there is an important distinction. A road surface becoming 10 degrees cooler does not always mean the surrounding air becomes 10 degrees cooler. Surface temperature, air temperature, and human comfort are related, but they are not identical. A highly reflective road may also redirect sunlight toward pedestrians or neighboring buildings. A porous surface requires water. Bright materials may create glare. Durability and tire wear matter. The best pavement is therefore not simply the whitest pavement. It must balance temperature, safety, visibility, maintenance, and cost. And sometimes, the fastest way to protect a pedestrian is not to redesign the road at all. It is to block the sun. Shade may sound less exciting than space-age paint, but direct solar radiation can dramatically increase the heat experienced by the human body. A tree canopy, covered walkway, or well-positioned roof can protect people immediately. The shade cools people even when the official air temperature remains unchanged. This is why a truly heat-resilient street needs layers. Reflective or cooler surfaces below, trees or structures above, air movement through the space, water where evaporation is effective, and accessible indoor cooling nearby for emergencies. China's traditional architecture offers another clue. For centuries, some homes in southern and eastern regions were organized around narrow interior courtyards known as skywells. The surrounding rooms shaded the lower space. Warm air rose through the central opening. Cooler air could be drawn through connected rooms and passages. The building used geometry, shade, and buoyancy-driven ventilation instead of relying entirely on mechanical equipment. The idea is not that every modern skyscraper can copy an ancient home directly. The lesson is more fundamental. Architecture can create air movement before a fan is switched on. A building's orientation, courtyard proportions, openings, and internal channels influence how heat and air travel. Modern designers can combine these principles with insulation, efficient glazing, and mechanical systems. The smartest building is not necessarily one that refuses to use air conditioning. It is one that needs far less air conditioning to remain safe. Now leave the building and return to the street. A thin white cloud hangs above a crowded pedestrian area. People walk through it without opening umbrellas. This is high-pressure mist cooling. Water passes through extremely fine nozzles and forms tiny droplets. As those droplets evaporate, they absorb heat from the surrounding air. The principle is simple. The limitations are equally important. Evaporative cooling works best when the air is hot and relatively dry. Dry air can absorb more water vapor. In humid air, evaporation slows because the atmosphere is already carrying substantial moisture. The mist may remain suspended longer, surfaces may become damp, and the cooling effect may be much smaller. This means an impressive result achieved under one set of weather conditions should not be treated as a universal promise. Water quality also matters. Nozzles can clog. Poorly managed systems may create hygiene concerns. Cities experiencing drought must consider whether using water for outdoor comfort is appropriate. But in the right place, at the right time, mist can be valuable. A shaded bus stop, an outdoor queue, a market where workers remain for hours, a station entrance where thousands of people pass during the hottest part of the day. The goal is not to cool the entire atmosphere. It is to create a small zone where the human body gains relief. This distinction is essential. Cities do not always need to reduce every outdoor air reading. Sometimes they need to reduce the heat received by the people standing in one critical location. Now imagine the remaining heat entering dozens of office towers, hotels, and shopping centers. The conventional solution gives every building its own large cooling plant. Each property purchases chillers, pumps, and cooling towers. Each system is maintained separately. Some operate efficiently, others do not. Shenzhen's Qianhai district uses another approach. Large central plants produce chilled water. That cold water travels through insulated underground pipes to connected buildings. Inside each building, heat is transferred into the water. The warmer water then returns to the central plant to be cooled again. The system can use large, optimized equipment and thermal storage, rather than depending entirely on thousands of smaller independent installations. Qianhai has also used ice thermal storage, allowing part of the cooling energy to be produced during lower demand periods and used later when the city's electricity consumption peaks. Local authorities estimate that the completed regional system can save around 130 million kilowatt-hours of electricity annually, compared with conventional arrangements. The infrastructure is nearly invisible from street level. The buildings still receive air conditioning, but the machinery producing that cooling has moved underground and become shared infrastructure. It is similar to the difference between every building operating its own generator and every building connecting to an electricity network. Centralization creates opportunities. Larger equipment may run more efficiently. Maintenance can be concentrated. Thermal storage can shift demand away from the most expensive hours. Future networks may integrate different energy sources. District energy is particularly valuable in dense urban areas, where enough buildings are close together to justify the pipe network. But there is no free cooling. The pipes are expensive to install. Roads must be opened. Buildings must be designed or modified to connect. Pumping water consumes electricity. Thermal energy is lost during distribution. The system works best where planning, density, and long-term demand make the investment worthwhile. A mature neighborhood of scattered buildings may be harder to convert than a new business district designed from the beginning around a central network. This reveals something important about China's advantage. Many fast-growing districts were built at enormous scale within a short period. That created opportunities to install infrastructure before every plot was fully occupied. It is much easier to plan one underground network before a city district is complete than to excavate beneath streets that have been crowded for a century. But what about cloud seeding? During drought and extreme heat, China has used rockets, aircraft, and other equipment to introduce seeding materials into suitable clouds. The objective is to encourage precipitation from clouds that already contain the necessary moisture and temperature conditions. It cannot create rain from clear air. It cannot guarantee that a specific neighborhood will become cooler, and proving precisely how much rainfall resulted from the intervention remains difficult, because weather systems vary naturally. The World Meteorological Organization continues to emphasize both the potential and uncertainty surrounding weather modification. Cloud seeding may support water resource management under certain conditions. It is not a reliable urban air conditioner. Presenting it beside reflective roofs and district cooling makes the story sound more spectacular, but it distracts from the most repeatable solutions. The most valuable urban cooling technologies are often the least dramatic. Shade, insulation, ventilation, efficient equipment, reflective surfaces, reliable electricity, cooling centers, early heat warnings, drinking water, protection for outdoor workers, and access for elderly people who may not recognize that their body is overheating. Wearable fans and neck coolers can improve personal comfort. Some use small fans. Others use thermoelectric plates that create a cool sensation against the skin. But these devices should not be confused with protection from dangerous heat. A cool feeling around the neck does not necessarily mean the body's core temperature is safe. A delivery worker wearing a gadget still needs water, rest, shade, and limits on exposure. Technology can assist public health policy. It cannot replace it. This is the most important lesson from China's urban cooling experiments. No single invention defeats a heat wave. The roof coating only protects the roof. The pavement only changes the street surface. The mist only affects a small microclimate. The district system only serves connected buildings. The personal device only helps the individual wearing it. But when these systems overlap, they can reduce risk together. Imagine the same hot day again. The roof reflects more sunlight. The building's design allows heat to escape. Trees shade the pavement. The road stores less energy. A misting zone protects people waiting for transport. Cold water from an underground network cools the surrounding buildings efficiently. A public warning tells outdoor workers when conditions have become dangerous. A nearby cooling center protects people who do not have air conditioning at home. That is not an air conditioner-free city. It is something more realistic. A city that does not force air conditioning to solve every part of the heat problem by itself. The hottest decades ahead will test every major city. Some will respond by adding millions of individual machines to buildings that continue absorbing more heat. Others will redesign roofs, roads, public spaces, and energy networks so those machines carry a smaller burden. China's real experiment is not about defeating the sun. It is about deciding where heat goes before heat decides how the city can function. The most successful future cities will not be completely passive or completely mechanical. They will combine ancient architectural intelligence with advanced materials, vegetation, public health planning, and efficient cooling infrastructure. And the final measure will not be how futuristic the technology looks. It will be whether an elderly resident can sleep safely at night, whether a child can wait for a bus without becoming ill, whether an outdoor worker can finish a shift without risking their life. That is what a cooler city is supposed to achieve. Subscribe for more documentaries about China's hidden infrastructure and engineering. And tell us below, which solution would improve your city most? Cool roofs, shaded streets, or one underground cooling network serving an entire district?